Now let's consider life in our backyard, the solar system. What can we say about biology in the solar system? Here we have an idea of life on Mars. Well, this is from the 1930s. It's actually Edgar Rice Burroughs, better known for his Tarzan series. He also wrote a sequence of books called the John Carter books, and they were based on epic battles between creatures and humans and other races on Mars. His vivid imagination created Mars as this epic place with obviously pretty ripped people there and pretty scary monsters. So the feverish imagination from science fiction that led seamlessly into the science fiction of Ray Bradbury and Robert Heinlein in the 50s and 60s posited that Mars was a habited place, perhaps not with people, but just with creatures, or especially maybe microbes. The reality was a little more mundane. When we eventually visited the planet with rovers in the 1970s, we realized that it was an arid desert. Cold, no liquid water could exist on the surface, an atmosphere 1% of the thickness of Earth's atmosphere and made only of carbon dioxide. Did not seem like a hospitable place. So, Mars riddled with life of the popular imagination, or Mars is an arid, sterile desert? The pendulum is swung back towards the middle a little bit, because there's now ample evidence in images like this from satellites around Mars that there was liquid water on the surface of Mars and perhaps shallow lakes and seas at least 3 or 4 billion years ago. Mars gradually dried out. Its low gravity could not keep an atmosphere, and eventually, with no atmosphere, the temperature got cold enough water couldn't exist. But these features that you see here are completely evocative of river deltas or shallow seabeds or places where sediments have deposited material over time. So there's strong evidence for water in Mars past. There's even evidence for water in Mars current and present in a set of images here taken by an orbiter showing on a rocky escarpment an episode where, we suppose, from a subsurface aquifer of water, water bubbled up and ran down a hillside. You can see the scale, 200 meters. This was about a swimming pool's worth of water, and of course as it erupted onto the surface and went down the hillside, it evaporated and froze almost immediately. But this is evidence that water exists on Mars right now, underground, where it can be kept liquid by pressure from the rocks above and by mild radioactive heating from below. So we think there's water on Mars now, and where there's water, carbon-based material, and a source of energy, there could indeed be microbial life. So Mars is a very promising place to look for life, which is why Mars is actually starting to get a little crowded. Where else apart from Mars? One of the interesting insights from planetary science is that moons of the giant planets are distinctive worlds in their own right, and many of them have the potential for hosting life. The largest of them have atmospheres and geological activity, and they're heated by tidal effects or from radioactivity in their cores. And that means that even though the giant planets are far from the sun, and so ostensibly far out of the habitable zone of our solar system, they could have localized conditions suitable for life. In fact, the best estimates are that a dozen of the moons of the giant planets might have water kept liquid under pressure below a rocky and icy surface. And this includes all the way out to Neptune. Even Pluto is turning out to be a little more interesting than we thought. Tiny Enceladus is only 500 kilometers across. Really an unremarkably small object, yet it has geysers that can spurt water into space based on an interior ocean. So we have to look at moons as well as planets as a basis for biology here in our solar system and of course elsewhere. And if we're looking at the problem in general, we can say that life does need energy, and that implies proximity to a star. But energy can come in other sources. It can come from internal heat of a rocky body, that's radioactivity. It can come by an elliptical orbit of a larger body, which is tidal heating. That's the squeezing of a moon, typically, by gravity in an elliptical orbit. And even if you need less stellar energy, you can also have thick atmospheres that can trap heat. So, when you need energy, there are different ways to get it. And it's worth remembering that the real estate in our solar system in what's called the cryogenic biosphere, that's the potentially life-hosting region that's far from the sun and therefore very cold, nominally below the freezing point of water, is much larger than the real estate in the conventional terrestrial habitable zone, which only includes the Earth in our solar system. So could there be life in even more extreme environments? People have speculated perhaps about biochemistry floating in the temperate upper regions of Venus's otherwise toxic atmosphere. Remember, at the base of its atmosphere, the pressure is 100 times of the air you're breathing, carbon dioxide and temperature hot enough to melt lead. But there's a temperate zone. Some people have even said that Io, the tiny volcanic moon of Jupiter, might have biochemistry based on a sulfur reaction cycle. That's very speculative chemistry, but people are allowed to speculate, given how little we know. And the context for this is remembering how well life does in extreme environments on Earth. We have found life near hydrothermal vents on the ocean floor in total darkness at temperatures of hundreds of degrees, that's superheated water, pressures of 100 atmospheres, and toxic chemistry. That sounds very much like Venus to me. These are entire ecosystems that do not use photosynthesis, so it's life that's independent of a star's energy. We've also found rock in the lithosphere, life in deep rock pores, which is also immune from sunlight, where energy is provided from radioactive heating and where water slowly seeps in from the surface or up from the core or the mantle. Here are some other places that are of great interest in the solar system. This beautiful picture was taken from an orbiting satellite several decades ago. This is Europa. This is the shattered icy crust of Europa, a water world completely covered in water and then crusted over with ice of unknown thickness, perhaps a few kilometers to as many as tens of kilometers. Smallest features you can see here about the size of a football field. And there's evidence, indirect evidence, that this ice shifts and moves around. It's in motion, although there are no places where liquid water is directly visible. This is what a cross-section of Europa looks like. And the challenge, of course, will be to send a probe far into the solar system to somehow diagnose what's going on this moon. It would be wonderful if we could somehow get below the crust. And in fact, there was an unfunded NASA mission designed decades ago where the idea was to land on that ice pack, use heat from a nuclear reactor to slowly melt through it, and then release a hydrobot, seen on the left, to explore the ocean for life. There are certainly maybe places where the icy crust is thin and water wells up and spreads over the surface. There's a Europa Explorer mission that has now been funded and will get there, unfortunately, in about a decade. It's a long way to go. And it won't do the lander and the hydrobot, but it will explore very detailed the surface, and it may have a part of its mission to splash off ice with a projectile and then sniff what comes off to see if it has biogenic elements in it or the basis for life. Here's a beautiful image, the only image ever taken of liquid on the surface of any body other than the Earth. This is Titan. This is a moon of Saturn. Evocative place. It's nothing like the Earth, although if you look at these images of lakes and river deltas and clouds, it looks Earth-like. But the lakes and the erosion are features of ethane and methane. This world is so far from the Earth, billions of miles from the sun, that the temperature there is far too cold for liquid water. However, ethane and methane can be liquid, and they're probably mixed with a little water and ammonia. So it's a complex hydrocarbon chemistry completely unknown to us. NASA's planning a Dragonfly mission, which will use drone-type technology to explore this world and sample these bodies of liquid, perhaps 10 or 15 years from now. A very exciting mission. If there is life on Titan, it would be life 2.0, because it could not have the same biochemistry as the Earth. And here, a very surprising object, Enceladus. This is the model of the cold geysers that we think are generated from some small amount of tidal heating and geological activity that acts on a pressurized pocket of water, not really an ocean, more of a small lake underground, and then vents to the surface where it ejects tiny ice particles. The Cassini mission has seen these jets and has actually sniffed the vapor in them, which includes carbon-based material. So again, this is a place very far from the Earth in a very inhospitable environment, which has all the ingredients for life. It could be a living moonlet. It's also surprisingly active for such a tiny body, which is because of its elliptical orbit of the larger planet. Again, this tiny world has all the ingredients known to be important for life: liquid, water, molecular building blocks based on carbon, and free energy. So if this tiny world in our solar system could have the ingredients for life, imagine how many places beyond our solar system might have the ingredients. And that's the end of this topic.